Continue with Salma Naimi moving now from India to Morocco all the way, and she will tell us more about Ab Initio Insights into the optoelectronic properties and stability of β-CuSCN as an whole transporting material for Perovskite Solar cell. Go ahead.
Hello, everyone. My name is Salma Naimi. I'm from Morocco. I'm jointly affiliated to Mohammed V University and Green Energy Park. I'm a PhD student, and I'm working on computational science and experiments. And my goal is to bridge the gap between these two fields. So here today, I'm happy to present a part of my work about inorganic HTMs. My talk will be Ab Initio Insights into the optoelectronic properties and stability of copper-2 as an HTM for perovskite solar cells. So during this presentation, I will adhere to the outlined plan. Over the last decade, perovskite solar cells efficiency increased from 3.8% to 27% in just few years. These devices are mainly composed from 5 different layers. Between them, the HTL or the HTM, one of the most gatekeepers of performance, and it's responsible for collecting the holes from the perovskite absorber layer and transport them to the electrode. So because of the energy level alignment, the HTM is responsible for extracting the holes and blocking the electrons at the perovskite HTM interface, and it also protects the perovskite from the electrode, which influence the GV curve of a device and also its long-term stability. So the problematic here is that the high efficiencies reached today with perovskite solar cells are using organic HTMs. However, these organic HTMs suffer from degradation and high optical losses, and also they are too expensive, as you see in the table. If we take, for example, one of the most used organic HTMs, which is spiro-omitted, it suffers from degradation, and here in this study from literature, you can see that the perovskite, the spiro-omitted layer, in the spiro-omitted layer, we can see that there are some voids that increase with increasing the temperature, which can lead to the perovskite solar cell degradation. So for the inorganic HTM, we use them because we can get high efficiencies without using dopants. They also are not expensive, so there is a possibility of commercializing this technology with cheap price, and also they have high chemical stability. What we want to do is that we screen different inorganic HTMs using the same approximations and the same methodology, so we can compare between them in terms of stability and optoelectronic properties. Then we link the properties of this material to device performance. So the used methodology here is studying the properties of materials, electronic, optical, and mechanical properties using density functional theory. Then we use molecular dynamics by applying Newton's second law of motion to calculate the thermal stability. For the results of this work, so after achieving the structural stability of our material, we calculated the elastic properties to confirm the mechanical stability of our material. As we see here, we noticed it from the bulk models and the shear models of our material we have a pull ratio which is higher than 1.75, which means that we are in front of a ductile material compared to our previous work on copper iodide, which we noticed that the pull ratio of copper thiocyanate is even higher, which means that our material, copper thiocyanate, can handle cracks if used as an HTM more than copper iodide. We also plotted the 3D plot of the Young modulus. We noticed that this material has a big anisotropy, which means that the softness of this material is direction dependent. So when we are in front of a material which is ductile and anisotropic, that's something that is suitable to use for an HTM. Here we calculated the Ab Initio molecular dynamics at room temperature over 60 picosecond. We found that the material is relatively stable. We increased the temperature to 800 Kelvin, and the material remains stable. If we compare this material to our previous work on copper iodide, we noticed that the copper iodide have more spikes in around the 300 Kelvin, which means that copper thiocyanate can handle high temperatures more than copper iodide. For the band gap of copper thiocyanate is a wide band gap of 2.7, which means that this material is transparent. And if we compare it to copper iodide, which also has a wide band gap, we notice that the copper thiocyanate can get more photons. That means that the photocurrent of our material, of our device using copper thiocyanate will be higher. Here we calculated the refractive index and extinction coefficient. So for this material, the refractive index is high at the ER indivisible region, and the extinction coefficient is low, which means that this material can minimize the reflection and parasitic absorption in the HTL perovskite interface. When compared to copper iodide, we noticed that the copper iodide has a refractive index higher than copper thiocyanate. That means that copper thiocyanate is less anti-reflective. Also, we calculated the absorption coefficient, which is relatively low in the ER indivisible region. Compared to copper iodide, the absorption of this material is even lower. Also, for the reflectivity of our material, it's low in the visible region. It's around 14%, and it reached a maximum at the edge, a maximum of 20%. And also, when compared to copper iodide, we noticed that the reflectivity of copper thiocyanate is lower. So some of our ongoing works is using the studied HTMs like copper thiocyanate in the same stacks, so to get the GV curve. For example, we used this stack with the copper iodide and copper thiocyanate, and we noticed that the PCE of copper thiocyanate is higher. We used another stack for both HTMs, and also this time the PCE of copper thiocyanate is higher, which is logic based on our previous results. So copper thiocyanate is a material that has a wide band gap, low absorption coefficient and reflectivity. It has the potential to be used as a low-cost HTM, and this strategy of DFT molecular dynamics and SCAPS is a general physics-based roadmap way to compare between inorganic HTMs. So if you want to connect, this is my LinkedIn profile. Also, in my Google Scholar, you will find my works about different HTMs, which were discussed separately. And also, this is my email. Thank you for your attention.